Okay, yes, we should begin. Welcome to the CITA seminar. Today's speaker is Laura Wolz. She's from University of Melbourne. Laura did her PhD from University College London and moved to University of Melbourne as a Castro Fellow. She's now an Australian Research Council Discovery Data Researcher Award Fellow there. Laura's specialty is H1 intensity mapping, and today she's going to tell us about how one can trace galaxy evolution with H1 intensity mapping.
Great. Thank you, and well done for pronouncing that title. Okay. Right, so I'm at the University of Melbourne there since 3 years, which is really fantastic environment to be in, especially in Australia these days with the SKA and so much radio stuff going on. And I'm going to talk about, I'm probably going to touch various aspects of intensity mapping during the talk, but mostly I'm going to talk about galaxy evolution. But if anything else kind of sparked interest, come and find me during the next week. I'm going to be here around till Thursday next week, and we can have a chat. I'm going to do a broad introduction, but I'm aware that probably most of the people know what intensity mapping is here, but I'm still going to do it anyway. So the motivation to do intensity mapping is that I think the initial motivation was that we want to understand the universe structure. We want to understand how the universe expands and how everything is distributed. And in order to do that, we really want to measure large volumes, and we need a massive amount of data. And that also means observation time to really map out all these big volumes. And if you do that with like galaxy surveys, you spend quite a lot of time to point of each galaxies, to measure their redshift, etc. So people came up with this idea that, well, if we would just not resolve all the structure, we actually still get a very good idea of how things are distributed. And from a cosmological point of view, that's totally enough, because we can still see a lot in this map, even if it looks horribly pixelated. You can still really see all the kind of like centers, clusters, and voids of this structure, and you can still infer a lot from this map. So what people have been thinking of in terms of observing strategy is that you take a radio telescope, usually a big dish, and you actually use that they have a quite poor resolution, because that will just give you a very pixelated big view like of how structure is distributed. And you just scan it over the sky and observe the 21 centimeter, the H1 spectral line. And like that, you can relatively efficiently really map big volumes of the sky, because every single frequency channel in your telescope will give you a different redshift of the neutral hydrogen. So by just pointing and scanning quite quickly, you get a lot of maps for every frequency and a really big volume that you can't really achieve with any other methods in the same amount of time. So these maps typically have quite low spatial resolutions in the maps. So you won't be able to identify any single objects. We won't spend any time resolving galaxies. But they do have a very high spatial resolution given by the telescope channels, if you have a sufficient signal to noise in these channels. I'm going to show you here two very extreme examples. The upper one is a simulation done for the SKA. This is very optimistic. Assuming we can observe the whole sky, we just have to kind of stop where the galactic center is, or our galaxy, because the foregrounds are terrible, so you can have these amazing maps of everything that's there in the universe, versus the GBT data, which started with a really small patch of sky, because it really was the first to observe with this method and to detect intensity maps. So you obviously started with smaller. So the advantages, or why people do H1 intensity mapping, one is that you integrate over the whole H1. So you have every single object that emits some sort of H1 or has neutral gas in it will be in those maps. So there's no selection effects in there, which can be very useful, because if you directly observe H1, you naturally just select very rich objects. And as I said, you can do these amazing tomographic maps. Basically, the SKA is planning just to do it for how far we can look until the appropriate ionization people take over, and we don't call it intensity mapping anymore, which is about redshift 0 to 6. And then with these really big cosmological volumes, you can just do many things you can think of, but the major one is measuring the baryon acoustic oscillation, or that was the major incentive that people thought of when they started establishing this method, that we can measure the BOOs, and through measuring the BOOs for so many different redshifts, we can really understand the expansion history of the universe. Tomographic map? Well, tomographic map basically just means that you have a lot of spherical maps out. So I think where this description comes from, you can imagine is like a CMB map, but just you have many of them for every redshift.
Usually it's when you take the same thing, you leave a projection probe but in different angles, so I don't understand the analogy here. Usually when you do a tomographic map, you take a picture, and it gives you a projection, but you repeat it, at least in medicine, so it's...
Okay, well, sorry, that's maybe then... I mean, we...
The analogy is that it's 3D, right?
Yeah.
It's a tomography in a CAT scan.
Well, yeah.
Cosmology is just slicing just to...
Yeah.
So it just means 3D imaging. 3D imaging.
Yeah. Thanks. Okay, so then what we do with these maps generally is that we measure a power spectrum to understand how the structure in the map is distributed. And this is theory, this is a toy model just to show you what can be done with. So there I've just plotted a fiducial cosmological model, and then I varied a few different parameters to show you what difference it can make, and to just, probably you're all aware of that, which all the different scales, what sort of measure the cosmological understanding the different scales can give you. So now from a general cosmology, like galaxy power spectrum, the difference for intensity mapping is mainly that the all over amplitude of this power spectrum will be in Kelvin squared, because the amplitude depends on the H1 brightness temperature of the maps, the average one. Which then this brightness temperature is just given by all the H1 that's in your maps, which is all the neutral gas. So it gives you the energy density of H1, which is something very great, and we have actually not a lot of constraints for that throughout the history of the universe. So that's the first thing you can get through measuring the H1, the intensity mapping power spectrum. And then, as I indicated, baryon acoustic oscillation, redshift space distortions, or any other like effects on large scales. Then there is this one, not caveat, but just also something that's quite intrinsic to intensity mapping. The resolution you get, or like what scales of the power spectrum you measure, depends a lot on your instrument. So with a single dish, you are sensitive to the very large scales. And with an interferometer, such as the SKA, you're typically more sensitive to the smaller scales of the power spectrum. However, if you have a compact array, which has really small baselines, that can obviously change a bit. But this is just comparison of single dish versus something like the SKA. So just to sum again, the objectives are first measuring H1 to really understand H1. Also measure how is H1 actually distributed with reference to the dark matter. So we want to measure the H1 bias on the power spectrum and understand the H1 distribution a bit better. Then there is this goal of having this SKA legacy map. So we just map all the H1 in the universe. And then we measure the BOOs to understand dark energy better, and measure the ultra-large scales, assuming that we get like basically an all-sky coverage. We can trace a bit more the nonlinear effects. And then also there is the possibility of doing cross-correlations with other observables. Mostly people think of galaxy surveys, but you can also think of CMB, something like that, which can then even get you more information out of both observations. So experiments. This is this is only a selected list. I'm sorry if I missed your favorite experiment in this list. First of all, obviously, Green Bank telescope. We all know that. A lot of people who've pioneered in this are here in this room today. Then the Parkes telescope has also been tried and tested, and now also successfully published the first detection of H1 intensity maps at low redshift by Chris. The paper came out last week. Pretty sure everyone knows that as well. So these are the two kind of dominant, really large dish telescopes which have been observing H1 intensity maps. Then there's CHIME, and a lot of people here involved in CHIME. But then there are also like other experiments such as ASCAP, the SKA Pathfinders, ASCAP and MERCAT, that are planning and can do H1 intensity maps, and then obviously also the SKA, which is planned. Here's a nice graphic again done by Phil Bull for the SKA science papers a few years ago, how the sensitivity to the BOO scale changes for the SKA. Because the SKA, the way it's currently designed with dishes of about 15 meters, and the baseline distribution that has been chosen is not ideal for intensity mapping, because as you see, basically for a lot of redshift, so this is the K perpendicular mode versus redshift on the y-axis, and here you can see on top the BOO wiggles. You can see that the single dishes are only, the interferometric mode is only sensitive to BOO for high redshift, but for the lower redshift, you actually need to use the SKA as a big number of single dishes, which poses a few difficulties if you want to do that.
For the baseline distributions, there must be a gap in the scales, right? Like, so the SKA doesn't have any dishes that are right beside each other.
Yeah. So you have these spiral arms, which are better for imaging.
So there must be a gap in the scales that you can do with single dish between single dish and interferometric mode, right?
There's probably a small gap that they might have missed. Yeah, sorry.
No, I'm just wondering.
Yeah, I don't know on the top of my head what the smallest baseline is.
But then back to the baseline.
I can totally look that up.
I need it from ASCAP. They're like 2 or 3 dish radii apart.
But that's ASCAP. I'm not sure if MERCAT is going to be the same.
SKA is a artist consumption, I gather. So
Yes. Well, I mean, the dishes, yes, of course, but MERCAT is being built, and it's going to be integrated into SK Mid. Okay, so that was the experiments, and then I also thought I'll show a few of these SKA predictions while we're talking about the SKA, just to get an idea what people are planning to do with these maps, or predicting, what's the motivation. So these predictions, I think, are all for the single dish mode, where you use all of the dishes as single dishes and just get great sensitivities through that. So this is a prediction done by Zeev Fonseca, and he has thought about how we can combine H1 intensity maps with optical surveys in the multi-tracer mode to then measure FNL better, and he has made these predictions. So the two colors are two slightly different models, but I do not know the details on the top of my head now. And the 3 different line styles are different, actually depending on the goodness of the optical galaxy survey you are cross-correlating with, where the worst is, I think, DES, the dark energy survey, and they make different assumptions, and then the best, I think, is for LSST-like data. And that way you can put constraints on FNL. And then there's this other, basically, precision cosmology. Phil Bull, as I already pointed out, has done a lot of work where he has kind of predicted how well we can constrain various cosmological parameters. And this is an example for the dark energy, where you have W0 and then WA. And here are in comparison, sort of like an optical is the red lines, or the red ellipse is like an optical stage 4, which I think should be Euclid-like observations, and then the blue ones is the SKA, which is relatively competitive, but then if you also combine these two, you get even tighter constraints, which for me is a lot always like, probably if we put all the data together, we're going to be the most successful. I've already mentioned that Meerkat is being built currently in the South African desert, and there are a few telescopes, I think early science, like not early science, but a few telescopes are already being tested as an array. And very recently, this paper led by Mario Santos came out, where he introduced the MERCLAS survey, which is the Meerkat Large Area Synoptic Survey. And there were a few science cases and forecasts for this, which should be probably beginning next year. And this is one forecast for intensity mapping, how intensity mapping using Meerkat can constrain the BAO wiggles for the different bands. This is the L band with a medium redshift of 0.3, and this is L band with redshift 0.9, where you can see that you can get really nice constraints there. And then also they have predicted the signal-to-noise ratio for the different bands for a couple of different observables, where A is the amplitude of the BAO, the baryon acoustic oscillations, dA is the angular diameter distance, and the Hubble rate and the growth. Where you can see here that the L band for redshift 0.3 is probably performing really well, except for the Hubble parameter, where probably you might achieve better results using the UHF band. So they're also doing this sort of like to get an idea which band is better to use than when they actually do the survey. So the survey is going to be here. So these plots are also against actually the survey area. So currently they're proposing 4,000 square degrees with 4,000 hours of observations. And this is still, probably the details are still to be determined, but this will be a really incredibly important survey for the SKA, because a lot of these like observation modes of single dish versus interferometric will be tested with Meerkat, because also Meerkat will then be integrated into the SKA1 mid array. So this will be quite something exciting to happen in the next few years.
What are the three colors? 3, 4.
That's a very good question.
Is it just n sigma with each color or something?
I am not entirely sure. I'm so sorry. I'll look that up. I just read it very recently, but nope. Okay, so now we're going a bit more into reality. Just one slide on reality for now. Why it hasn't been done, all of these amazing things, it's because it's really hard to do. There's a lot of challenges that come with intensity mapping. The first is there's very high receiver noise, especially in the single dishes, which you have to deal with. But if it's isotropic, we can deal with it really well in power spectrum space. There are any sorts of other instrumental errors that can become very significant if you try to do continuum maps. And you just don't, just do a single pointing and have a sigma detection. If you actually map out in a continuum, you can start interpreting any of these systematics as some funky cosmology. Then there's RFI, which is just really difficult to deal with. Parkes has a highway next to it. There's a lot of telephones that people use on the highway that you can see in data, which is not great. But thank God the SKA at least is in a very controlled environment. So the RFI plots that I've seen so far are really great, which hopefully should really minimize that problem. And then there are foreground contaminations, because we are obviously sitting in our own galaxy, emitting radiation, so we also have to deal with that, and there are different avoidance and removal strategies. I'm going to just touch on one very slightly, but if you want to chat more about that, come to me. Okay, so now we're going into the part of what to do with then H1 intensity mapping, and these are basically, what I'm basically talking about is a bit about the alternatives to all the cosmology I've just mentioned. Because just bear in mind, we're still looking at H1 cold gas. Intensity mapping H1 intensity maps should have a lot of information about the cold gas. And if we use them the right way, we should also find out a lot about galaxy evolution and learn more about that and not just only look at the BAO scales. So first I want to talk just about purely H1 evolution. You've probably all seen the left plot of omega H1, the energy density, as a function of redshift. These are all the observations we have to date, which also been added a few simulation points as the green data points. And you can see that the constraints are still not very tight. So there's still a lot of information to be added to this plot, which hopefully intensity mapping can do. And then it would also be interesting because at the moment, it's not quite clear how H1 really evolves over cosmic time and how much it is really correlated to functions like the star formation rate or the evolution of the molecular hydrogen. Then on the right-hand side, that's the H1 mass function. This is actual data in the gray plot data points from alfalfa and HIPAS, the two observations of H1 galaxies in our local own universe, which constrain very well how H1 is distributed in objects. And then the colored lines are predictions done by a semi-analytic simulation by Claudia Lagos, where they have also predicted the redshift evolution of this H1 mass function, which we also don't understand very well. And also it would also be nicer to extend, obviously, our observations to smaller masses. So this is, that's just a fit. No, that is a fit to the data points that they have done in the, which, exactly. So it is a bit, if it depends a lot on your model, which is, it's kind of making the point, you can fit a lot of things to these data points at the moment.
Like the star formation too, because that's definitely going up to high redshift.
Yeah, so, yeah.
I'm sure the fit would change if you exclude the point at 0 redshift. I'm not sure if that's what is causing the fit.
But the sun's in green?
No,
the green are just simulations, predictions.
The red point at 0?
Yes, but I guess those are the ones that we have actually the best constraints. So
that's the alpha.
Yeah. Okay, so this is what we know. And as you all seen, it could be much improved. So this is one of the incentives for one of the projects I'm involved in. We are now suggesting to do intensity mapping with SKA Low. So this is the low frequency array, which is built in the Australian desert, which is, most people just think of an EOR experiment, but it has actually a lot of sensitivity to H1 for the redshifts 3 to 6, where we think that EOR has finished by that time. And obviously, the EOR working group is not thinking much about these frequencies because they are still really trying to optimize all their methods and pipelines for the higher redshifts. So we are currently doing a bit of a project within the SKA cosmology working group. So I'm just really speaking on behalf of a lot of other people to make the case that we should really also get time to do intensity mapping at those redshifts, because as you've seen, we don't have many constraints for H1, and H1 intensity mapping is one of the few probes that can actually do measurements at these redshifts. So this is just a station layout that you can use. You can either use just the core area, so you have a lot of short baselines, or you can also use the central area, depending on what you want to do. And these are just kind of preliminary, quite basic forecasts, just how well you could do without including too much any systematics or something like that. So these, as the blue error bars, you can show how well we could constrain the H1 autopower spectrum. Then here it's sort of in the right plot, you can see the same autopower spectrum, just overplotted with the noise given by the instrument, the predicted noise. This is all for redshift, medium redshift 4, for a deep survey with I had the numbers on the slides before. So the deep survey is 5,000 hours observation time and 100 square degrees. And then these would be sort of like the added points that we could add to the omega H1 evolution plot. And you might say, okay, that looks all very optimistic and great. And we thought the same. So we actually, right now, this is not finished. This is really an ongoing effort to do proper instrumental simulations to really get a handle on how well can we do that and what requirements has our pipeline if we want to do that. And we do that. We also would like to find out how much information about H1 can we actually get out of the maps once we've done these observations. So we use different suites of simulations. This is an example where we use the Meraxis galaxy formation model, and this is just a nice simulation of the underlying N-body simulation of this semi-analytic model led by the Dragons team at the University of Melbourne. We have different schemes, so we can also partition the gold cast into H1 intensity maps, which is maybe not too exciting for you guys. And then we use a cube at redshift 5 just to start with for now to set up a pipeline, and we use the Oscar visibility simulator to simulate maps, how they could be observed using by different configuration of the SKA Low dish. And we also add foreground to that. And a lot of that work is done by Emma Chapman at Imperial College. These are the maps that we would get. So the green map, the green frame, is the PSF. I think we are looking at the central configuration for this plot, this slide. The one in the unfortunately, the reds look very similar. But so the one in the right top corner is the input H1 map. You can't see much on this because basically, obviously, in the semi-analytic simulation, the H1 is all like in galaxies, so it's points. Then on the left corner, you can see this is the H1 you would see if you just put basically the PSF on this simulation. So there's no instrument noise or foregrounds or anything on it, if you would have the perfect world, basically. And then on the right-hand side, you can see the foregrounds. If you put foregrounds in, this is actually the combined H1 maps plus the foregrounds. So obviously, you can just see the foregrounds because they're so much higher in amplitude. And then this is all these maps in power spectrum space, where we have, again, the same colors. Of the blue is the foreground. You can see much, much higher amplitude. Then the green is the PSF, and then the different red ones for the input simulation, and then also convolved with the PSF. So we are still working on that because we started with a very small area. These runs are quite computationally heavy. So we try to move then to bigger simulations to actually make a bit better forecasts, and also try to then remove the foregrounds. To remove the foregrounds, so this is my one slide, just a foreground removal, because I promised that in my abstract for some reason. To remove foregrounds, I use a method called FastICA, which we have tested on simulations, but also actually on the GBT data, and it seems to work quite well, which is a really nice blind source separation method. Has also been used for the CMB, since Renee nodded really heavily here. To remove the foregrounds from the signal. And it does it in this really interesting way. So it finds the components depending on statistical independence. So if you put a lot of components together and mix them all up, the probability distribution of these components will look very Gaussian. So what FastICA does is it extracts out components by sort of maximizing the non-Gaussianity of the PDF of that component. And what it cannot do, it cannot find Gaussian distributed components, which in our case is quite nice because that means it won't touch the H1 signal, basically. So it will just model everything that is sort of like non-Gaussian, like all the foregrounds. And then with kind of the error of this whole analysis, you end up with the H1 signal and the instrumental noise. But then if we can go to power spectrum space, we know the noise is just a line, ideally, and we can just remove it.
It's very well-behaved So you get a mixture of whatever distribution function you want, but it has to be well behaved. Do you know that the noise term is well behaved?
Sorry, what?
The noise component. Do you know that if it's well behaved? Does it have might have a heavy tail, in which case the central level theorem might stay?
So you mean with the noise, the instrumental noise?
Any source noise that you want to cancel this?
Yeah, I mean we have tested it and it works quite well. So yeah, we might want to dive in more details later if that's okay. So this is just incredibly preliminary, where I have just applied it to the SKA low, and then the yellow line comes from the foreground removal, but there's still a lot of tweaking happening, so I just wanted to give a very quick look into that. As I said, there's still going to happen more, and we will hopefully get some work on that out soon. And now I want to come to the galaxy evolution part of this talk. So now we looked a bit about neutral hydrogen evolution and how we can constrain it with H1 intensity mapping in which redshifts and which experiments. But then there's also, we would like to look more about on galaxy evolution. Can we find out more about this? So this is just sort of like data. What do we know about galaxy evolution? Well, usually what you want to understand about the life in a galaxy is what does the cold gas, or what does the gas do and what does the stars do, and how are stars forming in relation to how much gas is there in a galaxy. And then how does all of this evolve? And this is just a nice compilation of a very recent paper by Katharina Lutz et al., and where they've just plotted on the left-hand side the stellar mass in galaxies versus the H1 mass divided by the stellar mass. And you can see that there's a bit of there's a functional dependence. And this is just a compilation of a lot of different observations with many telescopes. And then on the right-hand side, it's again the stellar mass on the x-axis, and then the star formation efficiency, so that's the H1 mass quotient as of the star formation rate. Where you can see here, this is already a bit more, the picture is less clear what's happening there. And it's just really hard to determine what are the actual relations between these two quantities. And one reason for observations is that you have a really strong selection here on the H1 masses you can detect, and you're quite limited on where you can go with nowadays instrumentation. So there's only H1 detected for relatively low redshifts, and these are all have strong selection effects towards really rich objects.
All of these optical?
Sorry?
All of these data are optical data?
Well, H1 is from the radio, and the others is optical. So it's all the data that we have where you have an object, where you have both observations.
I think you can't use light mounting for this, or?
Wouldn't think so. Okay, so and then this is the same sort of view from a theorist, which you will probably not a theorist, but I call a theorist, someone who does simulations, where this is how you try to model star formation. So you relate the star formation rate to the gas surface density, which is sigma g. And it also depends a bit on the free fall time and efficiency in the galaxy, but then also mostly on the amount of molecular hydrogen that there is. So you have the whole cold gas, which makes the cold gas surface density, but then actually only the molecular gas is going to form the stars and the galaxies. And then there are different sort of, you don't need to dive into those details, but they're actually quite very different models how people choose to divide the cold gas into a neutral, like H1, and molecular phase. So you can either go by like a pressure type recipe or metallicity, which they both reasonably well work to compare. So there's still a lot of sort of data needed to put some better constraints on them, so we can actually also have a better understanding what all of these, what all of this really depends on. So now there's the proposal to use H1 intensity mapping cross correlations to actually observe these two things. So when you have H1 intensity maps, you often cross-correlate them with galaxy surveys, just from a point of view of getting rid of systematics, because you can get rid of foregrounds and any other like radio telescope instrumental effects by just taking a galaxy survey of the same volume and cross-correlating them. And that has been done and is quite successful. But actually also this cross-correlation will also have some galaxy evolution information in it, because you are cross-correlating a probe that was selected by the cold gas with something that was selected by probably the stars, like star formation rate in the different colors. So I've been kind of working on how to get that information back. This is an example of the GBT Wiggles data. This is where I've taken the data published by Kyo in this room, and just as the green shapes, and I've overplotted them by a semi-analytic simulations that I've been using to kind of show that they can replicate quite well the data. But also we have used 3 different models, which all kind of tell you, depend on a few different things. So why are the cross-correlations really good to learn about galaxy evolution? First of all, there's no selection effects in the H1. So you can actually really start probing sort of like the low H1 mass end with intensity maps through the cross-correlations. The shape of the cross-correlation power spectrum will be sensitive to that. And then there's actually this one thing, which is the cross-shot noise, which I will go into a bit detail, which is particularly, which will tell you particularly well about the H1 mass of the optical selected objects. I'm going to explain that better in a minute, just bear with me. And then when you have that, you can basically infer something like a scaling relation, which is really just what I've shown you in the real data, that you have here the galaxy sort of color, NUV minus R, which is an indicator for the star formation rate as a function of H1. This is just from a simulation. We are definitely not in a data measurement phase, but this is sort of what you can do. And then here's an example again where 3 different star formation models then give a quite different relation. So by measuring this, we can actually start distinguishing or getting a better understanding of star formation models.
Do you want to go back to the previous slide?
Yeah.
The blue, those are all the data points or simulations?
Yeah, no, so the green shades are the actual data. Because, yeah, and then the others are just simulations.
Oh, so this is H1 cross Wiggles, where the Wiggles is a simulation of
Yes.
Okay, great.
Thank you. No, I did not say that. We simulated a proper Wiggles selection to just really get sort of the similar, yeah. Okay, so I've just mentioned it, the cross shot noise. And I want to go back. Maybe this is a bit, I don't know, too comprehensive, but it took me a long time to understand the cross-shot noise, so I'm always assuming it might take everyone the same amount of time. So when you have just a galaxy power spectrum, there is a shot noise on it, which is simply the sampling noise or the Poisson noise, however you want to call it. So there will be a noise term, like just a constant noise term, which is just 1 over the number of samples you have, which is the number of galaxies. So this is that term, the number density. So it is just 1 over n. That's a shot noise on a galaxy power spectrum. Probably everyone knows that. It's very easy to deal with. You know exactly how many galaxies you've measured. So you just subtract that number to just have your cosmological power spectrum. If you were now to cross-correlate 2 different galaxy types in a power spectrum, if you would just divide your sample into like green and blue, and there's no overlap, you would not get a shot noise on the power spectrum, because they are all different objects. They are not in the same positions, so you don't get a cross-shot noise term. If you would now start to cross-correlate a mix, for whatever reason you're doing that, but who am I to judge? If you were now to get a mixture of green and blue and cross-correlate them just with the blue, the cross-shot noise would just be 1 over the number density of the blue objects. So the objects that are overlapping in the samples. Okay, so now we are doing this exercise. You see where I'm going now with the intensity maps. When we have intensity maps, we assume that every object has some sort of H1 emission in it, because they will have some cold gas. So now if you're now cross-correlating intensity maps with galaxies, there will be a shot noise, because most likely these objects are also emitting H1, so they are present in the intensity maps. So that means that the cross-shot noise will be proportional to the number of galaxies in your sample. That's great, that's easy, because we know that again. But in the intensity maps, each of the galaxies is actually weighted by the H1 emission, the temperature, the brightness temperature. So you get an extra term, which is just the medium temperature of the galaxies in the optical sample. So it's not the brightness temperature of the whole map, but just the brightness temperature of the optical galaxies. So that is actually a really interesting number, because that means I can take the intensity map and cross-correlate them with the galaxy sample, and I just get an idea of like the average H1 of that galaxy sample, which is probably something you have not observed with the telescope, because we can't for higher redshifts. And it might even be a very small temperature. So that is something that we can't observe really well as well, because their H1 mass might be really small in them. So again, this is the shot noise, just short again. Shot noise is proportional for that. You can now measure a shot noise if you go to smaller scales really well, because it will just be here like a constant. Your power spectrum will just converge to a constant, which is the shot noise. And you can just literally read that number off, which is really great. Or if you have only the bigger scales of the power spectrum, you might have to use a bit of different method, which I'm just showing a bit later now. This is a forecast for ASCAP Dingo that we have done, because ASCAP is actually also, because of the way the telescopes are distributed, is just sensitive to the relatively small scales of the power spectrum, which in first glance you're like, oh, then it's maybe not so great for intensity mapping. But if you think of measuring shot noise, that's a great choice, especially because it's overlapping, like the fields that are going to be observed with ASCAP Dingo. It's overlapping with a lot of galaxy surveys, which means you can do a lot of these cross-correlation measurements and get a lot of temperatures and H1 measurements for different types of galaxies. And here we've just shown that you can do it, hopefully in the next couple of years when the Dingo data is coming. This is again just showing, I'm a bit bad with time today, so I'm just going to skip that, and I think that's totally fine. This is just showing really quickly how we would measure these H1 masses from a cross-correlation coefficient. So we have the cross-power spectrum of the galaxies and the H1. And now if we only have the large scales of the power spectrum, it doesn't converge. So we kind of need to get to this number, this extra additional number. And then what you do is you look actually at the cross-correlation coefficient, which is the cross-power spectrum divided by the two auto-power spectra, which I've just shown there. But the power spectrum, the cross-power spectrum, has a little hat on because it actually has a shot noise term in it. It's not just the power spectrum, it's a thing that you observe. And if you were then to plot that number, you would get this graph where I've now taken, again, a simulation and divided it in loads of different galaxy colors, which is different star formation rates. And you can see here from blue to red that they look incredibly different, which is actually just due to the shot noise. Because if I were to remove the shot noise, which I can because it's a simulation, so I can just literally, I know that the H1 of these galaxies, if I were to just remove that, they all just come down to the same number. So this is just sort of like due to the shot noise, so you can formulate it like this. There is a way to fit this number, like from the cross-correlation, so you basically just need to make a prediction of how the cross-correlation coefficient behaves with scale, and then you can simply just fit it to the observed measurement, and then you get these dashed lines here to just get literally your measure of the H1 mass in each of these galaxy samples, and then you end up measuring a scaling relation like this. This is an example for quite high redshift 0.9, and you could really start understanding how H1 is distributed to the galaxy color. Yeah, so we have done a little paper on that if you want to read up on the method. And then I've also taken that a bit further. So in the last few minutes, I just want to show that you can also just really observe really the evolution of these scaling relations with intensity mapping, because we can do intensity mapping for so many different redshifts. You do need the optical counterparts for that, but again, you actually just need a small area overlapping. So for this multiple redshifts, I've taken a different simulation, the Eagle hydrodynamical simulation. This is just an Eagle simulation movie because I like movies and I think it's beautiful. And we have used the box of 100 co-moving megaparsec per H, and Claudia Lagos has provided us with a neutral hydrogen for all of the galaxies in the Eagle simulation, where she has used partitioning models. Again, these are based on the models that I've shown in the very beginning. And Gnedin and Kratsov and Krumholtz, and we have used this to then create intensity maps and cross-correlated them again then with galaxies that we have just selected from their different colors. And then this is the power spectrum that you would measure. This is redshift 0, where here are now the dashed lines, what you measure, because you have...
I'm afraid I've taken you back a long time. Could you tell us exactly what the partitioning model was?
Sorry?
I saw the name partitioning model, and I said to myself, I don't know what that is. But of course, everybody else in the audience does. Maybe you could give a brief explanation for what it is, since it seems to have also gone into this Eagle simulation as a way.
Yes, so that was the equations a few slides back. Let me just bring that up again. These ones. So you have these different partitioning models.
Why are they called partitioning models?
Because they partition the cold gas into atomic and molecular phase. It's just a term used.
Is the surface
So-
density of what? Gas.
So yeah,
H1 plus H.
yes. So the sigma G is the cold gas.
Is that gas? What is xenon?
Sorry?
What's capital xenon?
Metallicity measured in units of solar.
Thanks. So yeah, so we have this one which is metallicity based, which basically depends on sort of like how much, I think that the model works with how much UV comes in and like kind of partitions up the molecular.
Zero order thing because you don't have to believe either one.
And what's capital P in the
That's the pressure-based model.
expression?
That's pressure-based. So this one, the left one is a pressure-based model, and this other one is more about the metallicity and the UV background. So these are kind of both models come from a very different angle. And again, I totally agree. You don't have to believe each of them. They are just commonly used.
And so how it was used in the Eagle simulation is that they somehow made use of these magic formulas to say this is the amount?
This is the amount of atomic hydrogen, exactly, because the Eagle simulation just gives you the total amount of gas, and then you still have to put something, a model on top of that to decide of how much gas is atomic hydrogen, and how much is molecular hydrogen. And this is what is commonly used. These two models are in different flavors.
So we're using a more recent version, which is still not to be right? No, they're all bullshit.
No problem. Okay. Yeah, that's where we were. So yeah, okay. So again, I'm just showing, I mean, the same thing. I'm just using these models because they're out there and they're attempting to simulate what we're going to observe, and I'm just using them as like, well, that's how we could constrain them. That's a method. I actually don't really care that much how they look. It's just like, it would be amazing if we can actually provide data to say if they're right or wrong. Okay, so this is, again, here you can see it so much better, I think, on these smaller scales, how much you actually deviate if you don't, like the cross-shot noise, if you don't remove it or deal with it, this is what you measure on the dashed line. And then the solid lines are when you have removed the shot noise. And I think this should be a little movie where we're just going through the different redshifts. Where you can just see that this is just sort of an ongoing thing, so it should be relatively straightforward to measure the shot noise, and through that shot noise measurement, getting the H1 mass of each of these different galaxy samples. And you would end up with something like this. Again, so the Eagle KD is just one of these flavors of these models for H1. And then all of these different colors represent different redshifts. And these are sort of the different scalings that are predicted by eagles, and we could basically attempt to then measure them with this method by combining H1 intensity mapping with galaxy surveys and doing different samples in the galaxies.
Do you have an equivalent plot for the other version?
Sorry?
Do you have an equivalent plot for the other version?
I do have it, but not in this presentation. It looks very similar. There's actually, for the eagle simulation, it does not make a huge difference. I think because they're both so tuned to just give out what you wanted to give out. I don't want to be too critical. These people do amazing work. But yeah, it looks very similar. If you wouldn't see the name, I can't tell which one is which. This is what I want to end on. Basically, that H1 intensity mapping is not only a tool to do cosmology with, it will contain a lot of information about cold gas, and we should really do our best to use that information and to not just marginalize over any of these H1 biases or omega H1 or whatever it is. I think that we can really get the most out of H1 intensity mapping if we then also combine it with other galaxy surveys and any other probes. You always improve usually measurements, and you can really get completely new information if you do these cross correlations and do the interpretation in the right way. And that's what I want to end with.
So I want to go back to what everybody probably knows, but I didn't know well enough, that star formation rate tightly couples with color of galaxies. That's well known. And but surely, you know, if I have a bursty thing or I have a non-bursty thing, I can get more or less of degeneracy in color.
Yeah.
So that it can't be a perfect relationship.
No, I think it's the best thing to start with. I mean, I would say, this is stretching also my knowledge a bit because I'm not an expert on optical filters. But usually when you design an optical survey, you do have your set of filters, and you usually think very hard about what galaxies you are selecting with them. And I'm sort of trusting that whatever optical galaxy survey we are cross-correlating with, there will be an expert and who will tell me, well, we are choosing these galaxies for this and this reason, and we believe that they have these and these properties and these and these star formation states. Yeah.
So how much is the evolution of the metagalactic ionizing radiation an issue or an uncertainty there?
Can you say that again? Sorry.
The evolution of the intergalactic, maybe an issue or an uncertainty in these types of calculations?
Well, I did not think it makes such an influence for like these late redshifts. I thought that was much more an issue for in reionization models.
I'm thinking about, kind of the peak of star formation. Those are
moderately well measured.
But at lower redshift, it's not so well measured.
I think it's reasonably well measured.
One of the results of Chris's papers is that the H1 does, and we can measure the fact that H1 avoids red galaxies more than blue galaxies avoid red galaxies, right? And so that's kind of a bit of an indication of that, right? That you have this preferential avoidance. It's more than just sucking out galaxies.
It's more than what?
Well, and so the fact that if you cross correlate, Chris showed that if you cross correlate the red and the blue galaxies, you get a number on small scales. And then if you cross correlate the H1 and blue galaxies, you get something that you sort of expect. But if you cross correlate the red galaxies in H1, you get a bigger suppression, right? And so there's this that's saying that not that the H1 isn't.
The background doesn't matter. It's what galaxy you're looking at.
No, well, it does matter. So the blue galaxies are more strongly correlated with the red galaxies. I mean, so the H1 is correlated with blue galaxies, and the blue galaxies are correlated just fine with the red galaxies, but the H1 is not correlated with the red galaxies, which means that H1 is just avoiding those red galaxies, right? And that's something we measure.
Yeah, but what you're saying is that they don't have any H1 in them.
Not only they don't have any H1 in them, they don't have any they're pushing, the surrounding galaxies are being depleted of them as well, right? They're contributing to the background. Right? There's an avoidance that happens on the scale larger than the galaxy itself.
You don't know that that's true to UV from any of the galaxies.
Yeah, I mean,
I think we should probably
discuss this elsewhere.
Yes. Any other questions? Quick ones. I had a quick question. So probably a bit naive. Can you not use the alpha forest to cross-correlate your H1 cross?
You can probably. I've just never thought about it because.
You only have, well,
There's a dozen sightlines.
right. I mean, yeah. But you don't, at probably redshifts close to less than 1, you probably have quite a few quasars.
Well, I guess it's just much harder because you just have the galaxies. You know where they are. You know so much about them.
You also need overlapping fields, right? So that's another.
Anything that involves spectroscopy is too expensive.
Yeah, one last question.
so is SKA Low, is it capable of observing the OR bands and the redshift 3 to 6 bands simultaneously, or does that have to be done separately?
Yeah, that's a good question. I do not think so. I think we will have to have separate. I don't think I think it's a matter of computation powers, which is.
So the correlator just can't take the whole bandwidth, I guess, or. Mm-hmm.
Yeah, I think so, but I do not know the exact details, but which I'm not even sure if they're yet determined.